Hi everyone, my name is Pam Craven and I'm going to talk to you about my project for an ensemble to predict coronary heart disease. So the objective of my model is to create a predictor which can accurately predict coronary heart disease with as little as possible false negatives. The data set was obtained from Kaggle. It has 462 observations and 10 variables. Some of them are listed here. Our outcome variable will be CHD. My plan is to look at the RIPPR, the logistic regression, and support vector machines for models of a diagnosis. And I am evaluating based on accuracy, so the percent of correct predictions, false negative rate, the percent of patients wrongly diagnosed as no CHD when they should be CHD. And this is the most important evaluation in my opinion. The error rate, recall, and the kappa. And as you can see here, the data loaded, we have mostly numerical data with only one categorical. Also, we can look at the min and max and see some of the values like alcohol have a pretty wide range, so there might be some outliers here which we'll take a look at later. We have no missing values, and this is just a quick preview of the data set as it is. The next thing I did was plot the data and just look at different relationships. I'll just go through it really quickly because we don't have a lot of time, but as you can see here, we can definitely see some outliers between the variables, but nothing very linear between any of them. The only linear relationship I was able to sort of see was between obesity and adiposity, but you can definitely see there are some outliers here and there. I found out at the end of making my whole model that I needed to impute some missing values, so I just took a couple and I imputed the mean just to be able to show that I can do it. The next thing I did was do an outlier analysis using z-score normalization and a 2.5 standard deviations. So as you can see here, there wasn't many outliers, only a few from a couple of the columns, so I just removed them for simplicity. The next thing I did was perform a stratified split of the data, where 75% went to training, so most of it was for our training our models, and 25% was the testing or validation data set. I did a stratified split, so you can see here that our outcome variables are around the same proportions in both the training and testing data set. I also encoded my data. I did a dummy encoded a family history, so it was all numerical, and I also made my outcome variable as a factor. I performed min-max normalization, which you can see here. I just made a normalization function. I saved the max and the min from the training set and applied that to the testing set as well. Then I looked at the correlation and distributions. As you can see here, there's no strong correlations, positive or negative, between any of the variables except for maybe obesity and adiposity, which is at 0.7. If you look at the distribution of the data, you can see that there are some left skews, some stronger than others in SBP, tobacco, LDL, obesity, alcohol. We got a left skew in type A, and then our dummy variables and our outcome variables are just 0 and 1. So the next thing I decided to do because of those distributions was create a transformed data set. So I tried several different transformations, log, exponential, and square root, and I found that square root worked the best for my data set. So I separately transformed both the training and test set for tobacco, alcohol, SBP, LDL, and obesity. And I did the same for the test set and just saved them as a separate data set. And as you can see here, we have a better distribution, though not perfect. It is a lot better, and we're just going to see if it performs better. I also binned my data, so I made another training set to bin for the RIPPR model. And this is how I did it here. I made a couple different bin sizes. These are the ones that worked best for my analysis. The next thing I looked at was PCA. You can see here the correlations of the training set. Nothing crazy other than our dummy codes. And if we look at the components here, we can see about 50% of variance is due to component 1, and then around 18, and then around 11 for component 3. The scree plot also shows that first 3 components are the strongest contributors to the variance of the data. And COS2 variables for dimensions 1 through 3, you can see that the absence, present, adiposity, age, and obesity were the highest values for that. All right, we've just moved on to the rule-based model. And for time purposes, I'm just moving right to the summaries. But I looked at both the transformed, the original, and the binned data. And then I found out that the binned data had the highest accuracy and the lowest false negative percents. And so I used that to tune and perform hyperparameter tuning. I used a cross-validation of 5 and got the highest accuracy of 20.9. When I tried to do a cross-validation of 10 with some bags, it actually dropped a bunch and increased our false negative rates. In all of these, our kappa and recall values were pretty low, and the error rates were quite high, so we moved on to logistic regression in hopes that we could, increase our accuracy more and decrease our false negative rates, as well as our other evaluations. Just moving on to logistic regression, I'm just going to quickly jump to the summary. And here is the summary of the logistic regression models. And as you can see, the transformed data, which I thought was going to perform better, actually performed worse using just the regular GLIM function and no other types of tuning, 63% and 24% false negative. Overall, actually, our false negatives were higher than the Ripper model. The original non-transformed data did look better at 65%, and I did a couple different cross-validations. I did a lasso regression that didn't really improve anything, but when I did the cross-validations at a couple different levels, a couple different cost values, it didn't really give us any large increase in accuracy or any decrease in false negatives. Also, our kappas were lower, as well as our recalls, and our error rates were equally as high. So just moving on, I went to the SVM model. I'll just move down to the summary real quick. I tried a lot of different models for SVM. I originally looked at the vanilla kernel. You can see here that the accuracies are pretty low, but the false error rate is not terrible. I then ran the RBF on the original, transformed, and the normalized. The normalized did not do well using the RBF kernel. The original did better than the transformed data in this case. I tried to do a couple different tunings with cross-validation, and essentially the original and transformed data looked exactly the same. So then I moved on just looking at the original and doing a couple other different tuning things, but nothing really increased. In fact, this original tuning, I think I had a larger bag number, actually increased my false negative rate. So we haven't seen any huge jumps in accuracy or any really low jumps in false negatives. Again, the kappas for all of these were very low, recalls were pretty low as well, and the error rates were pretty high. So at the end of these 3 models, I decided I needed to look at a couple more models. So the next thing I looked at was KNN, and let me just show you that. All right, with the KNN, I just used the normalized data set that we created earlier. For the first set, I just ran a really simple KNN function, made a confusion matrix here, and just running it really quickly. You can see just out of the box, I'm at 67%, which is pretty good. Our kappa is the highest that it has been, and our false negative rate was actually pretty low. It was 14.7%, which is one of the lowest we've seen so far. So I went to look into tuning. I did train control using repeats of 5 and 5 for folds. I also looked at K values from 5 to 100 and did my metric as accuracy. And you can see here that our kappa increased pretty good, and our accuracy was around 68%, so it's looking a lot more promising. Our false negative rate was still pretty low, it was 15.6%. Not really where we want it to be, but it's a lot better. And our recall ended up being a lot higher than any of the other models that we had tested so far. So then I made another model and did repeats of 10 instead of 5, just to see if that would increase any of our accuracy at all. I'm just going to run it really quick. And as you can see here, our kappa does increase a little bit and our accuracy increases a little bit, but so also does our false negative. Our false negative is around 16.5%, but that's okay. It's still a lot lower than any of the other models that we had tested. So just looking at the summary here, really all of the KNN performed a lot better than the previous 3 models, and all of the false negative rates were much lower. So the last model that I looked at was naive Bayes. I'm just going to jump to my PDF. My naive Bayes, I ran with the binned data only, and as you can see here, the just initial basic run of the naive Bayes gave 63% accuracy, but a pretty low false negative rate. I did do some tuning with it where I was doing some cross-validations, and it did increase the accuracy, but between the 2 different tuned models I think I did different cross-fold numbers. It didn't really increase or decrease the false negatives at all, but still these were pretty good models as far as false negatives go. So I then moved on to the Ensemble model. I ended up looking at Ripper, SVM, the naive Bayes, and KNN, since they all had the lowest false negatives, which is the most important, and higher accuracy. I'll just show you here. In the end, we did get around 70%. We had got the highest kappa. We also got the highest recall of 0.7, was the highest we've seen out of all the models together. So it was actually an improvement. Let me just show you the code real quick. So here is the code. I have a mode function, and then within my actual function, I do normalize the data for KNN. I bin the data for my Ripper model and my naive Bayes, and then I call a couple different versions of the Ripper, the different versions of my KNN, of my naive Bayes, and one of the SVM. I then make it into a list and get the modes of each of them and return the list. And here is me running my test data and spitting it out. It took me a while to get all of the combinations that I needed, but it was worth it because I did see an improvement, and I'm just going to go to the summary. So overall, 5 models were tested: Ripper, KNN, naive Bayes, SVM, and logistic regression. 26 models were made total when you're looking at like all the different tunings and hyperparameters I was testing. In the end, the Ensemble did create the best combination of highest accuracy and lowest false positive rate, and also improved both kappa and recall and lowered the error rate. However, in my opinion, this model is still not good enough to test in patients. We would want the accuracy to be much higher. We would probably want the false positive rate to be like 5% or less, ideally like 3% or less. So I wouldn't suggest using this in any sort of production sense. I think it would probably be best to try and find a larger data set, or maybe even a more complex data set, in hopes that the training would increase our model performance and robustness. And here's just a summary of all of the models that I tested and accuracy and false negative, and you can see that the Ensemble is one of the best. The Ripper still had the best accuracy, but not the lowest false negative rate. And here's just my reference for my data and where I got it. It's been really interesting. I wish I could have come up with a better performing model, but I tried as much as I could to improve it, and this is what I could come up with. I think we just need a larger data set, maybe even with more variables such as gender or weight, things like that. But thank you for listening.